Welcome back. We are going to now start our scientific program with a lecture by Ming Li, who is a fresh, well, almost 1 year old faculty at Hampton University and is working double shifts this time as school manager and lecturer. So you're free to bother him for the whole 3 weeks. So, Ming.
Thank you. Right. Okay. So before I start, I want to do a quick survey by asking how many of you actually have taken courses on QED, either advanced quantum mechanics or quantum field theory, or maybe particle nuclear physics. You please raise your hands. Okay. Very good. Actually, the majority of you have exposed to QED before. So there will be 4 lectures. This is the outline of the lectures. Today, we'll talk about the fundamentals of QCD. So this is not, usually you talk about QCD like a semester course, but I'm going to talk about QCD in 1 hour. So it will be not covering everything, but the most important thing in my perspective. And I do not expect you will actually have some heavy derivations or calculations in this regard. The second lecture is, of course, I only have 4 hours. QCD is a very large research area, and I'm actually will focus on a very small area closely related to my research. I'm only discuss deep inelastic scattering. There are other high energy clearing processes and other research directions I'm not going to be mentioned or cover, and probably you'll learn a lot of other stuff during these 3 weeks. So the same process can be understood in 2 different regimes. So mine is the so-called Bjorken limit. I have 2 lectures on this, and the last lecture will be about the small x physics. These are the references when I prepared the lecture notes. So the first one and the second one are pretty classic on perturbed QCD about these factorizations and applications. And the third book is mainly about quantum chromodynamics at high energy, and which is another, in certain sense, it's known as a small x book, this one. The fourth one is maybe, since you already studied at least 1 semester of quantum field theory, you're pretty aware of this classic intro QFT book. And there's also, since the HUGS have 40 years, if you check previous editions to HUGS, there's very good lecture on introduction to QCD, particularly Janeway's lecture note in 2021. I find it's very comprehensive and covers a lot of topics. And of course, there's the particle data group, review of particle physics. You can find the experimental data and theoretical review on the topics of particle physics. And of course, these days, ChatGPT is always there. Okay, so quantum chromodynamics, some of you are familiar with the standard model of particle physics. It describes strong interaction involving quarks and gluons. So the fundamental degrees of freedom, QCD, describes this quark and gluons. So to build the theory of QCD, we need to start with the quark fields and the gluon fields. So for quark, it's a spin 1/2 fermion field. There are 6 flavors, so it's the index flavor, 6 flavors, and it also carries the color index which is labeled by this I, and it's in the fundamental representation of SU3. So in the fundamental representation, it's three-dimensional. For the gluon fields, it's a spin-1 vector field. It carries the Rollins index. We have 0, 1, 2, 3 here. That's the mu index. We have 8 components of the gluon fields. There are 8 colors. And you can imagine it will be an 8-dimensional linear space. That's the adjoint representation of the gluon fields. In QED, we have the abelian symmetry U1, which is related to the electric charge. And in QCD, that's the non-abelian SU3 associated with the color charge. So this, the so-called quantum chromodynamics is the dynamics of the color. Color is the quantum number describing strong interaction. SU3 is global symmetry. So under this, the so-called symmetry is a collection of transformations that when you make such transformations, the system is invariant. So for quark fields, you can transform using this this gauge transformation, and this little TA is the generator of this SU3 global symmetry. In quantum mechanics, we have the SU2 group, which describe the spin, right? The spin dynamics, spin 1/2, you have the 3 Pauli matrices, right? So this TA, TB is the SU3 version of the Pauli matrices. So I think maybe we should just mention this. So these are the generators of the SU3 group. If you look at, this is, of course, this is one basis. If you look at the structure, you can recognize that, oh, this lambda 1, this upper corner is basically the Pauli matrices. But now it's because it's 3-dimensional, you need to add additional row and column here. And if you look at the other 3, if you ignore the central row and column, you also have the 3 Pauli matrices there. And of course, and then you have 2 additional generators. And you can imagine this is more complicated than the Pauli matrices describing spin. Okay, back to the global symmetry. So this generator, when you exponentiate, you get a transformation. So you basically form a linear combination of the generators with some constant theta A. You have the SU3 group transformation here. For the quark field, it's basically just the 3x3 matrix multiplied by the quark field. For the gluon field, it can be combined with the, because it's in the adjoint representation, so you also have 8 generators, but it's not 3x3, it's 8x8 now. And its transformation is given this form, but it's a matrix multiplication in the 8x8 dimension. Its operations, they do not commute. So you perform a rotation around a certain direction in the color space, and then you rotate around another direction. You will get completely different final state if you reverse the order of these 2 operations. So it's a global symmetry, of course, meaning that your theory should be invariant under this symmetry. By the way, if you have any questions, please stop me. I'm not sure how too fast or too slow, or actually it's too abstract, or you can make the analogy with SU2 that you can understand some part of it. Yeah.
If you go back to the previous slide, what does the FABC represent here?
Actually, that's in the next slide here. This FABC is the total antisymmetric structure constant. So I think in the SU2 case, you have the Pauli matrices, and you have this. You have this. This is also the structure function in the Pauli matrices. This is the totally antisymmetric constant. Here, because it's so SU3, you have 8. Your ABC can be taking the values 1 to all the way to 8. So you have a lot constants here. That's the structure function. And most of the time, we don't need to know exactly what these values are. And if you do a calculation in QFT, basically you have the combinations of color matrices. Most of the time, you will take a trace because you will not observe the color quantum number. You sum them. And in other cases, you probably just keep the matrix structure of the color matrices. All right, so that's the global SU3 symmetry, meaning that this transformation is independent of the space-time. But to get the interaction or get interaction between quarks and gluon, we need to promote the global symmetry into a local symmetry, meaning that my SU3 transformation need to be space-time dependent. So I can perform this color transformation independently at any space-time location. In this global symmetry, it means all the color transformations have to be the same because it's a constant. It needs to apply to all the space-time. But this one, you can individually apply that at particular space-time position. As a result, this gluon part takes, because it's space-time dependent, then it has this additional nonlinear term here, which contains a derivative on the gauge transformation matrix because of the space-time dependence there. So with the promotion of global SU3 symmetry to local SU3 symmetry, one can introduce the interaction between quarks and gluon by simply replace the ordinary covariant derivative with, ordinary derivative with the covariant derivatives. So this also happened in QED. In that case, you don't have the matrix, color matrix structure. You only have the d nu minus ij a mu. That's what happened in QED. But in QCD, because it's SU3 is 3 by 3 matrix space, so you need to multiply by the generators of SU3 transformation. Then the usual Lagrangian for free Dirac field or quark fields is replaced by the covariant derivative. In this way, one generates a coupling between the quark field and the gluon fields. That's basically how the interaction between quarks and gluons is introduced. Okay. This local gauge symmetry also not just determines the dynamics of quark and the gluon interaction, it also determines the dynamics of gluon field. So in QED, you only have the field strength tensor, you only have this first and the second term, but in QCD, again, you need to have this nonlinear term here. The reason is to make sure that the whole theory will be gauge invariant, SU3 local gauge invariant. That in other cases, you might see that, oh, this is you can write this in the matrix structure. Write this as the commutator between two matrices. If you write this in a component form, that's basically what you have here, because it explicitly carries the color index there. So you have write this F mu nu A, everything will be, because a matrix, so it will be a matrix multiplied by the SU3 color matrix. And also for this term, and then you will have the commutator of two matrices, and that gives you the using the structure function, structure constant, SFABC there. Then you can form this is also very naively is the same form of the QED Lagrangian for photon, except now it carries it needs to sum over all the color indices A there. So this is a form of the ground self interaction in QCD. Okay, with that we can write down the QCD Lagrangian, which is the first part is by promoting the ordinary partial derivative into covariant derivative that gives us the interaction between quarks and gluon, and then generalize the field strength tensor to contain the nonlinear term that not only gives us the kinetic term for gluon field, it also introduced the three gluon interaction term and the 4 gluon interaction terms. So based on very simple principle of local gauge invariance, it completely determines the form of strong interaction here. So it's actually a very powerful principle of the nonlinear gauge symmetry. The next few slides is essentially about explicitly checking the. It's a double check what you already obtained here. So we construct this QCD Lagrangian by requiring local gauge invariance, and we introduced the fields and the covariant derivative here. And the next few slides, I probably should not go through this in details. Basically, it double checks if I now recall what the SU3 local gauge transformation for the quark field and gluon fields, and then I substitute into my QCD Lagrangian. I just want to double check that it is indeed local gauge invariance. I'm going to skip this. Actually, these are just plain algebra. You have a transformation here. You just make sure that the primed form is exactly the same as the unprimed form, for example, here and here, and they are gauge invariant. The Lagrangian you constructed is indeed local SU3 gauge invariant. So any questions so far about the construction of the Lagrangian for QCD? Okay. Well, so we used the local gauge symmetry to introduce interaction between quarks and gluon, and also the self-interaction gluons. But this so-called local gauge symmetry is not it's not a physical symmetry. is a redundancy of the field description. So what I mean by physical symmetry is the SU3. The global symmetry is a physical symmetry because it's the color. And the local symmetry is what we used to construct the interactions. It's kind of a prescription. Somehow, yeah. Okay, I'll just move. So global symmetry is a symmetry. Local symmetry is not symmetry. That's basically the message. So it's not a symmetry, it's a redundancy of the field description because we use the vector field to describe the gluons. It contains 4 components because your mu can be 0, 1, 2, 3. But you all know that there are only 2 polarizations. So a photon, and there's only 2 polarizations. So there's gluon. Gluon is also massless. So actually, you should only use 2 components to describe this gluon, like you describe photon. But you want to use 4 components. There's a reason for why using 4 components. The most important is, of course, everything you write is manifested Lorentz invariance or covariance. You want your theory to be to respect Lorentz transformation or that's but it introduces redundancy, and you need to do the so-called gate fixing. There's a general prescription or a series of steps to do this. You can find in almost every QFT book. So you do gate fixing, and this is usually done using path integral approach. Then it will generate the so-called Faddeev-Popov determinant. And then you need to promote everything to the Lagrangian. That's how you actually introduce the so-called ghost fields. These are auxiliary fields. They are not physical. They are not physical field. There's no particles called ghost. It's more like you introduce some redundancy, you need to fix your redundancy. That's basically the ghost fields. Because if you have a redundancy, you have some, if you do quantum corrections, you have some non-physical fluctuations there you need to fix. So the gate fixing here, this term, so the first 2 terms are the QCD Lagrangian, and then we introduce this gate fixing term. It can take different forms depending on what kinds of gauge you want to work with. In the covariant Lorentz gauge, this is usually d mu, a mu term there. And the last term is the ghost interaction term. You have the ghost field C and C bar, and interacting with your gluon fields. This is non-physical. It's Grassmann fields, looks like a fermion fields, but it's actually interacting with the gluon in the adjoint representation. So it's auxiliary fields. You introduce it in your field, in your theory. And there are 2 types of this. C is a free parameter. You can choose either 1 or 0, and it recovers the well-known Feynman gauge and the Landau gauge there. Yeah.
So one question regarding like this fluctuations. So basically, this fluctuations appears because of the 2 non-physical degrees of freedom of the gluon field, or
Yeah, it's because of the,
Okay, so basically the ghosts are introduced to cancel this non-physical things that appear because of the non-physical degrees of freedom of the gluon.
sort of.
Okay.
Wouldn't setting xi equal to 0 have a 0 in the denominator?
Oh, you don't set it here. So you usually, okay, yeah, we have the propagator, and you set this, usually once you have the propagators, you want to do the calculations. Okay, because, yeah, anyway, that's, in practice, that's how we do it.
I'm gonna ask kind of a naive question, but is there a reason why people like covariant gauges over like an axial gauge? Because to me, like axial gauges don't have ghost interactions with the gauge field, right?
Right, usually in certain gauges, we don't have the ghost.
Right.
That's probably.
I've only ever used Lorentz gauge too, so I don't know. I've never known why. So
In the axial gauge, you choose one particular direction. It's kind of not, it's not Lorentz invariant. You pick some particular direction, it's not rotation or both days is not invariant. You have to, but it's useful if usually if you are doing high energy collisions, you have some preferred direction. For example, if you have two beams, they are propagating this way, and then you have the beam direction that is kind of the preferred direction of your setup. You can certainly do calculations. Actually, I usually use like light cone gauge, and yeah, and I rarely use the covariant gauge in my research. So, but the general theory and most of the the traditional perturbative QCD is done in the covariant gauge because Lorentz invariance certainly is played a very important role in the development of the whole standard model theory. So, yeah. Once you have the theory, the Lagrangian, you can write down the Feynman rules. You have the quark propagator, which is the same as in QED. Now you have the delta function for the color indices. Similarly for you have the Coulomb propagator, and because of you also have the additional gauge fixing terms here in addition to this G mu nu, and you also have the ghost propagator. It's kind of a scalar. It carries a joint color index here. Then you have the quark Coulomb vortex, similar to QED, except now you need to insert the color matrix in the fundamental representation. And then there's this ghost Coulomb vortex. So it's momentum dependent, and it's dependent on the adjoint representation of SU3. So it's momentum dependence because of this additional derivative there. Then this the three-ground interaction vortex, also momentum dependent, and then you have the four-ground interaction vortex there. Okay. Well, so that's the, if you try to use we have the theory, we have the Feynman rules, you can calculate scattering processes, you can draw a Feynman diagram and start to do calculation. Tree-level calculations are finite, are fine, but once you start to do some loop calculations, For example, this also happens in QED, this ultraviolet divergence in QED. Basically, you have some loop in your diagram, you need to integrate over the full momentum. And when the momentum goes to infinity, your integral diverges. So you need to take care of these divergences. And this divergence is from the short distance quantum fluctuation, which is the region when the momentum is very large. So the divergences is, so this is the usual renormalization, like in QED. You need to absorb these divergences into the redefinition of fields, mass, and coupling constants. The reason conceptually is because, okay, I just showed you how to construct this Lagrangian step by step here. I have this final form, but when you try to do calculations, you try to relate this to some observables. And very naively, you would think, oh, I have this thing describe, this field describe the actual gluons and actual quarks, and this mass is actually the mass of the quarks. But that's not the case. These are the so-called bare quantities. You are doing the construction purely from some principles or theory, as U3 gauge symmetry. They are not exactly the same as the physical mass or physical wave functions of the quarks and gluons. So what we wrote down is the so-called bare Lagrangian of QCD. So everything will be denoted by subscript 0, meaning that these are some quantities if I don't know anything about experiments or any measurements, I'm a theorist, I want to follow in certain principles to write down the interaction of the Lagrangian QCD. Then I wrote these things down, all the zeros, but they are not directly measurable. And if you try to make a connection with experiments or data or reality, you need to connect your theoretical construction with the reality, these fields, the physical fields, or couplings or mass, which is also called renormalized or, right, they are called renormalized fields and coupling. So they are related by a multiplicative renormalization factor, usually denoted by Z, with some, these 2, 3 are conventions. Historically, these are conventions, how they are defined. And the Z is also called wave function renormalization. And you also have the mass renormalization, coupling constant. Everything in your bare Lagrangian will be related to your renormalized Lagrangian, and then they are related to the its renormalization factors here. So it's like a redefinition of what you constructed previously. Now you can express everything or your bare Lagrangian in terms of renormalized Lagrangian and something left, which is called counter term. So the form is exactly the same. Now it's just, oh, I don't call these fields 0 anymore. Now they are real physical or renormalized fields, mass, and coupling constants. And the counter term is the difference between the previous bare Lagrangian and the renormalized Lagrangian. So I'm left is exactly the same structure. It's just that now I have the difference there. Again, the fields are now in terms of the physical fields, and right, these the so-called conterms will be determined order by order in perturbative calculation to cancel your UV divergences is achieved by absorbing these UV divergences into all these different types of renormalization vectors there. As you can see that the delta Z2 is essentially just Z2 minus 1 because you redefine your fields and then you subtract the term 1, which is the term 1 here. And then that's the counter terms is essentially the difference. And these coefficients for each term, they are not exactly, not all of them are independent because you still need to make sure that your whole theory is still gauge invariance. The gauge invariance will put some non-trivial relations between these. They look like there are many, but not so many there. I think with that, this is basically the final form of QCD Lagrangian with the counter terms in terms of physical fields and also the counter terms there. So when you actually do a calculation, beyond the tree level, not only you need to like the previous diagrams, you also need to draw the counter term diagrams and make sure that your counter term diagrams will absorb your UV divergence order by order. That's basically how the renormalization works. Any questions? It's like a very clear procedure people developed. So next, I'm going to talk about the. So the theory is given by the Lagrangian. Next, I want to talk about the most important feature of QCD, which is the running coupling and the asymptotic freedom and the confinement. That's basically the topic in the rest of this lecture. Usually, when we do renormalization, we need to first to regularize our divergence. We cannot just put infinity there. We need some parameter to actually parameterize the divergences there. The most common one is dimensional regularization. So instead of working for space-time dimension, you work in some non-physical dimension, which is less than 4. In the end, usually the divergence will be given by 1 over epsilon square, and all these pools. And in the end, you set epsilon to 0, and you go back to the physical space-time. If you're working in the non-physical 4 minus 2 epsilon dimension, you can work out the mass dimension of the fields. The important thing is your coupling constant now is not a dimensionless constant anymore. It carries a mass dimensional epsilon. So when you try to define the relation between bare coupling constant and physical or renormalize the coupling constant, it's convenient to actually factorize out this mass dimension there. So it carries dimension of energy to the power of epsilon. So I just write it down there, write it explicitly, so that my renormalized coupling constant is dimensionless. Of course, this is something I introduced kind of like a bookkeeping object, and the physical observables in the end should not depend on this arbitrary scale I introduced there. So the running of the coupling constant is characterized by the so-called beta function. It's defined in this way as a first order derivative of the coupling constant. In this d equals 4 minus 2 epsilon dimension, you have the relation between bare coupling constant and renormalized coupling constant. And they are related to the renormalization factors. All this is some combination of Z1, Z2, and Z3. I'll just shorthand notation Z alpha here. So you can require that this bare parameter, bare coupling constant is independent of the scale here. If you require the bare coupling constant is independent of mu, you get an equation that relates to the derivatives of the renormalization factor with the derivative for your physical renormalized coupling constants. Because the whole operation is done in the 4 minus 2 epsilon dimension, so you can actually similarly define the beta function, and then this beta function is related to, you have the epsilon dependent term, which comes from the explicit scale dependency, and you also have the derivative of your renormalization factors with the scale there. And then if you take epsilon to 0, you recover the original definition in the 4 dimension. From this, you can actually, I'm actually gonna skip this probably, if you are interested, you can carry out an exercise by first performing the expansion of the renormalization factor and then compare terms by term. You reach the conclusion that to determine my beta function, I only need to focus on the single pole of the renormalization factor there. So if you want to calculate this, you focus on that. You just need to isolate this single pole there. At one loop order, this is the alpha has this very simple form. This is not simple. Okay, if you want to do this calculation, it probably will take you many hours to actually get this result, but it is simple in this form here. It's simple in the sense that it was Nobel Prize work back in 1973. They calculated the beta function back then. But at the leading order, at one loop, it is simple, and you can substitute back into the expression here. You get the beta function, and you notice that this beta 0, which is related to the color factors of SU3, in this form, this NF is the number of flavors. So we have 6 flavors of quarks. So you put 6 here, so you get a positive value. But you have additional this negative sign in front of this beta function that basically tells you the asymptotic freedom, which is different from QED. This is the elementary simple differential equation. You can solve that. This is the form. Q is some reference scale you put there. Typically, people choose this, or experimentally, it is determined by using the mass of Z boson, which is 92 GeV, and this is very this is pretty determined value of the coupling constant is around 0.2 of the at Z boson mass. Again, so basically this is saying that because the flavor is less than 17, you have you look at this expression. If your mu goes to larger and larger, your alpha S goes to smaller and smaller. If you have a negative sign here, you will get the opposite. Right? That's basically what happens in QED. As I mentioned, that there's a very interesting story there. Two groups of people, they are actually working independently, and if you're interested, you should look up what happened then, back then. Another important information from this exercise is if you try to I think the message here is there's a dynamical scale generated. If you look at the expression there, I should. Let's see, I'll finish this and then I'll finish lecture 1. So basically back to the equation here. So you have this alpha, you solve that, you rewrite it in this form. Q is a reference scale, so you basically take the inverse of that expression. Then you get beta 0 over 4 pi, and then you get log mu square over Q square. Now you try to, so this is a reference, like when you do integration, it's like integration constant, right?
Sorry, do you have a darker marker?
Let me see. This one is better?
Yeah.
This one. So you have this 1 over alpha as mu. This is a scale dependent. When you do the integral, you have this Q part. Then you have this log mu square or Q square. Right. So this is the integration constant. Now you want to try to redefine that in a form very similar to the second term. But this time you want to put it as lambda QCD, some scale with Q square there, with mu square there. Sorry, I made some mistake, not mu square. Sorry. Basically, you put a Q square there, and you have this lambda QCD. So you have a dimensionless quantity, but you have a scale Q there. You need to introduce some scale there because you don't want to put a dimension for quantity within your log. It has to be some dimension there. You put it there, you get this alpha as mu. And then you have beta 0 over 4 pi. And then you get mu square over lambda QCD. Here, and then you rewrite it in a form, basically, that what it happens here. You have this you have this additional, you have this new scale, QCD is related to the original Q there. That new scale basically tells you when your quantum fluctuations become non-perturbatively important, that's a scale separating when your perturbative calculation breaks down, and that's basically the scale of lambda QCD. If you can use this to do estimate Q square. If you remember, we can put this Q as mass of Z boson, and these are well determined. You can put it in this expression, you get a value of lambda QCD. If you do this naively, you won't get 0.2 GeV. You'll get other larger numbers. But if you use the, 5-loop calculation of beta function, numerically, that will give you a number pretty close to 0.2 GeV. That's the lambda QCD. So approaching this lambda QCD theory is strongly coupled, and the quarks and gluons are confined within the hadrons. So this, of course, is the success of experimental measurements and theoretical calculations to confirm our understanding of the running coupling of QCD. Two messages. One is asymptotic freedom, and the second is confinement scale, a dynamically generated new scale there, separating perturbative and non-perturbative. Yeah, that's all for lecture one.
Very much. Any questions?
You explain like attributed QCD measurements where it is possible, like for higher energy regions, right?
Can you repeat the
Uh,
question?
At higher energy regions, perturbative QCD measurements are possible, right? Is my question is right?
You're asking if it's possible to do QCD measurements in high energy regime?
Yes.
So what do you mean high energy? You mean the energy at the CERN, like I don't know, 14 TeV or
Between 10 to 100, maybe less than 100.
between 10 to 100? These are from different observables. Like if you look closely, this is from particle data group. You have the green. The green data is from E plus, E minus, these jets measurements. And you have also the blue part, which is from higher jets measurements. So these are probably in the probably in the 12 EM process, E plus, E minus jets. I'm not sure higher jets what they are here. Oh, they are. But this x-axis is not the clearing energy. It's some hard scale, the virtuality of your process. If you have E plus, E minus, you have virtual photon. That's the virtuality of your photon, probably. So this is the resolution scale, probably. That's what we should call it.
What about the small x regions? You didn't talk about small x.
Small x.
Yes.
Oh, that's the topic of the last lecture. So I'm just telling you the fundamentals of QCD, which is no matter what physics, particular area of QCD you want to study, these are the basic theories and the two important properties of QCD that I just described.
Any other questions?
Could you repeat why you had to go to lower dimensions to be able to, or why you went down to lower dimensions when you're talking about, I guess it's on slide
Oh,
20.
you mean the dimensional regularization?
Yeah, to do the renormalization.
Um,
Why did you have to do that? And then also like, why does that change the dimensions of the coupling constant?
Okay, so because we want to regularize, okay, this, let's see. So if you have we are concerned about the UV divergence, meaning if you have momentum, you have a beta marker. Oh, this one looks better. So you are doing, okay, maybe 40. UV divergence, usually you are concerned about factors like this, because if you put an infinity, because dimensionally, this will be k square. If your k goes to infinity, it will be a problem. But if you try to lower the values here, minus, it's well reduced this to something. It's well reduced. The dimension there will make it less severe. If you are dealing with infrared, when the region goes to 0, you probably are more concerned to put this as a plus there. That's how you regularize. Your second question regarding that dimension of G, the coupling constant is in the term of you have this. You have TA, then you have this A mu A. So this is the coupling part in the Lagrangian. The whole thing, so this integration measure should have a mass dimension of force, right? Meaning that this whole object should have, okay, now we are in D dimension, sorry. We are in D dimension, the measure is D. So the whole thing here should be, okay, this is 1 over D, so the dimension of this whole thing should be D. You put the dimension of percent here. So you have 2%, 2 quark field, you multiply that gives you 3 minus 2 epsilon. And then you have 1 A field, which is 1 minus epsilon. And then you should add your dimension over J, which is some unknown. Plus that should be give D, which is 4 minus 2 epsilon. Right, so then I end up with my J is the mass dimension is epsilon there. That's why I have the epsilon there. How do you know that? These two, you can use the part of you can use this. This is also a mass dimension D, but you already know the derivative is like is 2. So that's how you deduce the dimension of the vector field. And similarly, you can use there's a kinetic term of your quark field to determine mass dimension of your fermion field, which is 3/2 minus epsilon. And then you can use that to determine the dimension of the coupling constant. Okay. Thanks.
Okay, any other questions? Seems not the case, so we can have coffee break now.